but it's easy actually. It's not difficult. So don't worry. So we are going to talk about superconducting qubit, and then we need a more formal treatment on the quantum mechanics, right? We need to use further quantization or a second quantization of quantum mechanics, so all the operators. So before that, we will talk about the so-called Lagrangian and Hamiltonian mechanics. Today, I hope that I can finish the Lagrangian, at least the introduction. We have been learning Newtonian mechanics, at least for EE student, right? I don't think we have learned Lagrangian and Hamiltonian mechanics, at least I did not, right? We use vector, right? We use vector, we say, okay, you give me the force, I follow F equal to ma, I can determine how every particle will move in this universe by just tracking F equal to ma and the Newton's law. That's called vectorial mechanics. There are two other approaches which is more convenient, very important. Like the physics people will learn in their undergraduate class called the classical mechanics, right? That they use scalar approach. They discuss the energy. They start with the energy formulation and do minimization, right? Or action or whatever. Something we look at that differential equation. They came up with the same equation. And that is very easy for difficult problem because we have something called generalized coordinates, generalized velocity, generalized momentum, all these concepts. And we will see how good this is, right? So the first thing we'll do is Lagrangian. But why do we need this? That is because for Hamiltonian mechanics, we can move from classical mechanics directly to quantum mechanics by just promoting the operator in Hamiltonian mechanics to promoting the quantity in Hamiltonian mechanics, in classical Hamiltonian mechanics to operator, then you will get the quantum version of that system. And then you naturally will get the quantization of the simple harmonic oscillator. More importantly, you even get a quantization of the electromagnetic field. So this path, of course, is very profound in math. We won't go into those, but we just learn the skill. You don't need to understand why. But learning those skills will prepare you for the future if you want to go deeper. Otherwise, it can already help you to appreciate how to solve a superconducting qubit. Because superconducting qubit are using some quantity that is not in our real space. It's very difficult to appreciate. It talks about the charge, the phase, etc. of the qubit. So you cannot appreciate if you don't learn this. So what is Lagrangian mechanics? So this is the same also for other things, but here we introduce something called generalized coordinate. So all you need to do, just treat it as a regular coordinate like qi. For example, in our real 3D space, i's can be R1, 2, 3. Okay, X, Y, Z. But it's not just this coordinate. Later you find in your assignment, right? The coordinate can be just the angle. You treat the angle as a coordinate. Okay? We also have something called generalized velocity, which is not difficult to understand. Of course, velocity, we know this in our real everyday experience, right? Q dot, I have a dot on top of it, which is dqi dt, right? And why these three are this quantity are important, right? If we know qi and qi dot, if you give me 1 trillion particle, you give me their position and velocity at a certain point of time, and I know what is the energy landscape. I can predict its past, I can predict its future, right? If these two quantities are specified, then the system is determined. Okay, do you agree? Now, then we also try to learn something we just take it for granted, okay? So it say that there's something called the principle of least action. So what does it mean? First, we define, right? We say every system can be or is characterized by something called Lagrangian. It's just a name, don't worry. And the symbol is L. And this Lagrangian depends on Qi, Q1, Q2, Q1 dot, Q2 dot, means that it depends on the coordinates, depends on the velocity, but it's not just the coordinates and velocity in our real world. It includes the generalized coordinates and generalized velocity, and also the time. Okay, so if you say, okay, this system has this Lagrangian, you will expect it is dependent on all the coordinates and all the velocity. Okay, and also the time. Coordinate and velocity are their independent variables. Qi dot are independent variables. That's the first thing, right? The first thing. But more importantly, this principle of least action also says something. There's something called action, just a quantity. We call it S. It's the integral of the Lagrangian. Okay. Of course, this is Qi dot, and T, it depends on this, over time. From T1 to T2, there's something called action, okay? So you just have system, you take it for granted, you have action. And then you just integrate it from a time to another time, okay? That's just a definition, right? Action equal to this. And it say that action is minimized from T1, it is minimized for a state evolving from T1 to T2. Basically, what it says that, hey, this Lagrangian, how do you find this Lagrangian? It is difficult. However, this Lagrangian should be that when you do the integration from T1 to T2, it should be minimized. So what does it mean? For example, I have this one just a hand-waving argument, might not be complete. For example, I have a ball going in this direction. And I have different friction. I have two regions, A and B. Because it has different friction, of course you can go through the Newton's law and solve how it will move, right? But one way you can do is that it can go like here, go straight from this point to this point. It can also go from this point to this point. So what is the equation of motion? It turns out that it cannot be from this point to this point, because if you try to integrate the action correspond to this system, this is not minimum. And turn out maybe this is minimum. And this can be used to explain the refraction of light also. Why when the lights go from air to water will get refracted? And basically the path is choose, if you go through the calculation, is the shortest time you can reach from the shortest time you can reach. Maybe I should do this, right? You may also talk about this. Why it will choose from this point to this point? Why it will follow green? Why it has a refraction? Because going from this point to this point, following the green path is shorter than you go through a straight line from here to here. Because the lights have different speed in different media. You thought that this is a shorter path, but actually this is longer because this one on this region, it travels slower. Do you see what I'm trying to say? Just a hand waving example, right? But that is the meaning of action. It turned out that the system will evolve such that the action will be minimal. Okay, so if you just look back, right, you look how the particle move, you actually try to look at its action. Indeed, you integrate it. This is the smallest. You say, hey, maybe this is another action, another formula. I try to do it. You find that it cannot give you a lower S. This is not going to be tested in the exam. It's out of the scope of this topic, of this class. But I just want you to appreciate a little bit why Lagrangian is so important. Because you see that it is the foundation of the whole classical mechanics. Because you describe everything by minimizing the action. You can derive all the equations by just saying that I need to minimize the action. And you need the Lagrangian. That's why it's so critical, okay? So we can forget about this if you are not interested, right? But now we go to the heart is, I want to finish this. Lagrangian, we just say that the Lagrangian of a system, L, as I said, it is a function of the position. Now I just put a vector because you can have many positions. A function of the velocity and time. And it's also the total, the potential, the kinetic energy minus the potential energy, T minus V, of the system. Kinetic energy minus the potential energy. This one is easy to understand, right? This is just a definition, right? Don't worry why you do that, right? And of course, the kinetic energy depends on what? The velocity, right? We are thinking about the real 3D space. But then it is true when you go to a generalized space. Minus the potential energy. Potential energy only depends on the location, right? Potential energy does not depend on how fast you move. Of course, it depends on the time. Okay? So then, from the least principle, the principle of least action, we don't need to know it. Don't worry about this. But I just let you know how you get this. From principle of least action, we can derive, but we don't derive this equation. D dt partial L partial Qi dot minus partial L partial Qi equal to 0. And this is the famous Lagrange equation. This is what you need to put in your cheat sheet. So I could have just give you this at the beginning, right? And this is just what you need to know. I try to derive a little bit. You see that this is a partial differential equation relating the velocity and also the position. So if I'm three-dimensional, how many equations do I have? You just do substitution, right? For example, it's 3D I actually have three equations. So it's a system of three equations. Why? Because I have d dt, right? Let me do it simple. Partial L, partial x. No. Let me just call it V1, not x. V1. Partial L, partial x equals 0. I have d dt, partial L, partial V2. Partial L, partial y equal to 0. The third equation is d dt, partial L, partial V3, minus partial L, partial z equal to 0. Make sense? So you need to go through all the i's. So you have, let's say you have 100 particles that you want to track. How many equations do you have in 3D space? Each of them has how many degrees of freedom? They're called 3, right? 100 particles, it means you have 300 equations. Okay, just appreciate this, right? So you don't need to learn anything here. Just appreciate we have Lagrange equation. This related velocity to position, so it means by solving this equation, I know how the particle move already because it gives me the relationship between position and velocity as a function of time. That's why it's so useful, okay? So I think time's up. We continue next time. Any question from online?